said. We're trying to improve component files so that you don't see file damaged, and the principal case where you can see them is if APL gets interrupted whilst it's updating a component file. There have been two stages to the work. John has done all the work that I'm going to describe first, so I'm not taking any credit for this. And this is already in 12.03, so the first part of this you can benefit from now. And then afterwards I'll briefly introduce you to additional work that I'm doing, which will be in a future release. So I'm going to bring up John's favourite diagram. We think of a component file, or we can think of a component file like this washing line. It's a collection of different items arranged in a line. And conceptually, the file is done in exactly this way. It's a linear string of components which you can access or remove or replace. But in practice, we don't maintain the file anything like this, because if you tried to replace a small component with a larger one, we'd have to shuffle everything around on the file, and it would take forever. So while we do try and keep all the components in one piece on the file, we scatter them around, and we use a tree of indices to find them. So I will show you what we actually do using this representation. Here I'm representing a file, and I'm going to use this through virtually every slide with this line with the beginning of the file on the left-hand side, and anything which is unused in the file, the free space shown in pale blue. The important thing to bear in mind is that anything which is unused is unreferenced, and APL never looks at it. So anything in there is garbage, and we can do what we like with it, which is an important concept for later in the presentation. At the moment, what we do is every component file has a global information block at the start, and this gives us information about such things as whether it's 32 or 64-bit and how many components are in it. And then we have component index blocks. These are the representing the tree nodes. These tell us where the components are. They're quite efficiently arranged in that each block can point to either 16 components or 16 other index blocks. It's actually a B tree. And so you can very quickly scan through those to get the location of an actual component. Then we put the actual component data itself. Here there's 3. They're not in any particular sequence, as you can see. And normally there would be gaps between them as data was written, and they would taken away. These gaps would close up. And finally, every piece of free space has a little node at the start of it which links all the free spaces together. And again, we can search through these very quickly to find a piece of free space that we need when we're updating the file. So if I illustrate what happens when you do update a component, here we've got a component, a single component on the file, and we want to replace it. So we'll come along, we'll write the new data into free space, and I noticed that when I did that, the free space node was overwritten because it was part of the free space, but it was there. And then we update the component index blocks. So now the component index points to the new component, not the old one. And then we update the free space nodes, which has freed up the old space, and we update the root. And similarly, if we're adding a component, so this is, it's not for me. If we're adding a component, very similar process. We write the new data. We have to choose some space, and here we'll choose the space the old one was in. We've overwritten the free space node again. We update the component index blocks so that we've added in the pointer to the new component. We update the free space nodes, and we update the root, and we're done. Now, you may have spotted the flaw in this, and that was the fact that we overwrite the free space node all the time. So we're going to do this process again, and I'm going to show you it going wrong. Here we've started writing the new component. The free space node has been overwritten. We kill the APL process, and now we've got a free space node which has been referenced from elsewhere in the file, but it's been corrupted. So this file is damaged. So to solve this, and this is the part which is in 12.03. We do use journaling. As I've said, the free space in the file contains nothing which APL will ever look at, so we can play with that as much as we like. And when we make an update, the majority of it is in free space. The component occupies free space. The only part which doesn't is the bit which would override the free space node. So everything else we write into a journal, and then we complete the update as normal. So I'll show you the update again. This time it's journaled. We can update the free space. There it is. We put the journal somewhere in free space. We write most of the component, but notice this time we've not overwritten the free space node. And then we write every other thing into the journal, just a description of what we intend to do, the rest of the component, the component index block, free space nodes, and the root. So what we've done now is we've only updated the free space. We haven't actually changed this file at all as far as APL is concerned. And yet at the same time, the entire update is described within the file. We now activate the journal, which means that we put a pointer from the root to it. This lets us know that it's there and where it is. We execute it, we run the things which are described within it, so we complete the update. And we're done. Now, the advantage of that will be obvious when we look at what happens when we access a journaled file. In this case, in all cases, we must check the existence of the journal. And in this case, the previous update completed successfully. So there's no journal there. So we just carry on accessing the file as we would have done. And in this second case, we're partway through the update. You can see that we've written some of the journal, but there's no pointer to it in the root. So everything that you see, everything that you see is in the free space. There's no pointer to it in the root. So effectively, there's no journal at all. So again, we just carry on. Now, what's happened here is that we've rolled the file back to a safe position. Have you been catching me all right? Oh dear. Have you been able to hear any of it up to this point? Good, okay. So we've lost the update as a result of APL being killed, but we haven't damaged the file. And in the final case, this time we have a journal. It's been referenced from the root, but we got killed at some point when we were executing it. So the file is very damaged indeed. So we've checked for it. We re-execute the journal because we have the description there of what was supposed to happen at the point APL was killed. And then we remove it. The file has been repaired and the change rolled forward, and then we can carry on. So brief summary. This is in 12.03. They'll protect the file from damage if APL is killed. They have very little impact on performance and size, just the extra writing of the journal. But you can select whether you want this on a per file basis. You can journal some files, leave other files unjournaled. By default, they are not journaled. So if you do want to journal them, there is a new property to quad fprops. J1 will enable it, J0 will disable it. You can switch backwards and forwards as much as you like. And when you've done that, the file is used in exactly the same way as before. There's nothing you need to do. You just get better file security. Yes, it's sticky to a file. It becomes a property of the file. Yeah, it doesn't affect all files that you then create. That's what I meant, because I thought you initially were going to ask. Now, just note the downsides, because it's important that we check that the journal is present when we access the file. It's no point throwing one of these at any earlier version, because they won't know what to do with the journal. So, in fact, you cannot access them at all with an earlier version. But if you need to do that, then just turn journaling off. So as I described, if APL is killed, you're protected. However, there is a however, that's not always true if the operating system is killed or there's a power failure. And that's where I've come in and I've been working. The reason that happens is because when there is a power failure, the writes to the disk don't just stop. Some can just magically disappear. And I'll explain why. It's to do with disk caching. So I've got this funky little diagram. I've got the APL process writing data. It goes through to the operating system, which caches it. And then the operating system, in its good time, will write it out to the disk. And the advantage of that, generally, is that APL doesn't have to sit and wait for the data to get on disk. It can carry on running pretty much straight away. And the operating system, or indeed the disk hardware, will optimize the writing to the disk platter in the most appropriate way, wait for the disk to spin round and so on. So they're held in memory, and out they come, first, second, and third. And they're going onto the disk, you'll notice, in the wrong order, because that's the most optimal way of doing it. But it doesn't matter, all of the things are there. And even if APL gets killed, first, second, and third writes come out. They go onto the disk, APL's died, but they still all get onto the disk. But as you can probably extrapolate forwards, if you kill the operating system, out come the first and the third, but now the second has not made it to disk, and we've got an out-of-sequence data loss. And everything that I've shown you before has a requirement that things happen in certain orders. Now let me show you an example of where it would cause things to fail. You saw the journaled update before. We write everything into free space. And then we write the journal as present. So at this point, if we were to tie this file, we would see that there was a journal which had to be executed, and we would go ahead and do it. But supposing we got to that stage and there was an operating system crash, and that particular part of the journal happened to get lost. When we tried to recover that file, we would have a corrupted journal, and we would actually cause more damage than was there already. And during any update, there's 4 of these cases. Now, for this afternoon, I'm just going to tell you what they are. If you're more interested in why they're there, the original slides, which are on the memory stick, have additional pages which will explain them, but I've found that I'm not going to get through everything, so I'm just going to tell you that you must atomically write to the free space, mark the journal as present, then execute it, and then remove it. And if you get losses between those 4 stages, we will not be able to protect the file. So if any of you know fsync, you'll immediately be asking why we're not using it. Fsync is an operating system function which causes a wait until data is actually physically on disk. And that means, if you see in this example, APL is forced to stop whilst the data gets written. And as a result, everything is getting on disk in the right sequence, so we wouldn't have this problem. And 4 fsyncs per update would solve the problem. But the problem with fsync is, as you've seen, it causes a wait. It causes a significant wait. Updates to files slow down by factors of about 1,000. So this wasn't an option. So we've been thinking about something else. Now, what we discovered is that, in one of the cases that you saw just now, if we had a broken journal, we would corrupt the file. So if we checksum everything, we checksum the component and we checksum the component and the journal, we can tell that there's been damage, and we won't execute it. So 2 fsyncs can be eliminated at once by doing that. So we're down to 2 now. The other 2, well, we can say, well, we'll leave those fsyncs out and the file will get damaged. So what can we do to repair it if that happens? And what we can do is we can add some redundancy to each component, and we can use the checksumming we've already needed to go through a file and find all the components and rebuild all the indices, because it's only the indices that get broken if the file gets damaged. But there is a slight problem with that, in that if you remove all 4 fsyncs, you've no idea how much data will get lost if there's a crash. 1 fsync will guarantee it's only the most recent update, and you might not want to lose more than 1 update. So what we need to do is give you 3 journaling options. ones that have 0 fsyncs, 1 fsync, and 2 fsyncs. And the additional cost of running the fsync will buy you the convenience of never having to repair the file, and the knowledge that you only lose at most one component on an operating system crash or power failure. So, this is the work that I've been doing. It's not. It's in development, and it will be on a future release. Because of these fsyncs, it could have a greater performance impact. If you choose the no fsync option, it should have virtually none. And also, it will have a slight impact on the file size because we're going to make each component slightly larger so that we can find them and repair the file. Oh, I'm sorry. And again, per file, you can choose which journaling you want. Now, this might be particularly useful because there's a performance impact. You don't want all files to be journaled really slow, to be really slow. So we'll allow you will choose the ones that are really critical to have maximum safety, and temporary files may not have any journaling at all. And again, you won't notice any change when you actually use them. They'll continue to use journal files in exactly the same way that you do now, component files. And we'll provide this one additional tool, which currently we're calling quadfjuk. This will be built into the interpreter and be a function. And on a operating system crash, you run this tool. It will check the files that were open at the time of the crash, and it will look for damage, and if it finds them, it will repair them. And that screen tells me to stop. Yes?
I've been recently a user of external files. I don't know whether that was a good choice. But external variable.
Right, yeah.
But is there anything connection between the issues of...
If you wish.
At the moment,
my more general question isn't about this, but how would I learn whether I can tell the choices of external files at all?
I would say some variables are
That sounds like an answer that I should have really convenient to back to.
Yes. Oh, who's next? Go. Yeah. Well, you remember at the beginning I showed appending a component and replacing a component, and then the process was almost identical. So the work that's been done will be beneficial in both cases, and the problems exist in both cases. Yeah. If there's no journal, it will skip all that, but it will check if it's a journal file. But it will check whether it's a journal file in the first place. So. Adrian.
right, because if your machine crashes, you just would restart with that as well. So you have to, it's a tool. You have to choose between
Adrian. Well, this was the earlier testing which was done. In fact, with a network drive, fsync happens automatically. It would appear from our experimentation, so you get less benefit. Fsync happens at the end of the write, or on the file close. Yeah, at the end of the write. We were getting less benefit on remote files anyway. It was already fsyncing. Pardon? The journaling is important, and it has lower cost. It has lower cost. Yes, that's true. Yes. Go ahead.
How did you create the crashes in order to test the code?
Can I refer you to Dan still there? Kill -9 anyway was essentially this. I will qualify this by saying that this bit, the testing of the bit that's now there, was before my time, but it was basically kill -9.
Yeah, but you do effectively, usually I would leave it running over the weekend, so it would be statistically, you're hoping the variation will hit kind of work in the space. So effectively, I was getting probably every second or so, starting the process, starting up and it was fine, you could tell from the bug curve, slotting my code out, I'd miss everything in that bit. And then, it started fine. And then suddenly it was on all the weekend and Jim was not able to do it. So it's nothing. So the real-time programming is very difficult to test physically. But it was not like city today, but it's a question typically.
Well, that's more of what John said. It's a scatter shot.
Yeah.
But that's harder to do, 60 times a minute.
Yeah, we will do cases like making the component of the thing fall over by putting code in, but then it's only the things that we think of. The scattergun approach is random, but it's thorough.
We can do other techniques where we can see the area of the code and use the code failure onto the now we have these
Well, there's only ever one journal, and it's a transient thing which exists only during the update.
Well, no, it exists on the file, it's just a crash, and then when we retire the file, it is a journal, then it can be re-executed as a file server.
Right. Yes. Yeah, this will be an automatic process. Yeah. Yeah, go ahead. Don't mind.
Within a component file, there are two distinct trees. One tree locates the component. Okay. Within a component file, there's components and pre-threads, and then one tree locates the component, and another tree locates the pre-thread. They're independent entities. So if the component index tree is intact, you can read all of the components. If that's broken, you'll get a file damage on read. Likewise, if the tree is damaged, you get a time space on the file that goes down there. So you're right, sometimes it just happens that if you're running J0, no journal, or tree version 12, it happens that you may not be able to attend to the file and that's just lucky. And what you should do in that case, what you should do now is put journaling on. But if you start attending to a file with damaged tree journal, you can start more than that. So if you've got a tree journal, it's kind of that's a really good practice. I'll give you another one. The codex read size on a Dyalog component file compacts the file. It moves all of this stuff down to the bottom end. So you use one free block on the end. It's file compaction. And the pre-journaling file compaction took a deep breath and slid these blocks. I don't know if we got one with a blue bit, but it actually slid the blocks down one after the other and then scurried around and fixed up the quantity. Now, if that went wrong halfway through, game over. Yeah. But the journaling codex read size moves one block at a time. It takes slightly longer, but you can not only can you fill a task for that, and it's still okay. It may not be completely compatible, but But you can actually do a strong intro in the quality site on the journal file, and it will stop what it's doing and come back and produce. So that's the space operation. That's a very good point, yeah. Yeah, the reason it takes so long, if you've got a large file, it's doing all the stuff and everything